Hi, my name is Donna Dietz. I teach at American University. Previously, I also taught at Mansfield University, which is in rural Pennsylvania, kind of near Corning, New York. And I taught a non-Euclidean geometry course there. So this discussion I'm going to give is informed by both groups of students, the non-Euclidean geometry undergraduates, who are mostly pre-teachers, and the general undergraduate population at American University who's taking Gen Ed math enrichment type courses. I came up with the idea for this talk because the joint math meetings is going to have a contributed paper session about origami, but it's really geared for K through 12, and I wanted to gear this talk for undergraduates. I'm going to first talk about a little bit about construction, but then I'm going to talk about the various things you can do with these objects once you've made them. There should be some objects circulating around the room. Just pass them around and enjoy them, feel them, yeah, just enjoy looking at them. Okay, first of all, there's some written instructions. I didn't make them, but I made this tiny URL for it because I happen to like these instructions. So tinyurl.com/sonobe, and it's some really good instructions and pictures on how to do that. I also have videos on YouTube, and I'll show you later how to get to those. For my Gen Ed courses, I spend at least one class period, sometimes two class periods, just discussing these things and walking around and making sure everybody has the basics. If you spend, whatever time you spend in class, the students still have to spend about maybe an hour outside of class working on just the folding and the assembly. The project I'm going to be talking about is the one that's based off of the icosahedron. You see circulating around the room, there's some smaller objects and some larger objects, but most of them are roughly the same size, and that's the one that's based off of the icosahedron. That one takes 30 pieces of paper to make. The first big issue you encounter is the chirality, or the mirror imageness. You have to kind of see the difference between the letter S and the letter Z. If you can do that, then you can do this project. But you get really confused sometimes if you start the project, stop folding for a while, and go back to folding, and you accidentally start folding them all in mirror image. Because then what happens is you have 30 pieces folded, and you've got like 14 of one and 16 of the other, and then they don't fit together. So chirality is a real big important point for this project. This is the paper I use in class because it's a very nice paper, but it's not origami paper. A perfectionist will notice that it's not perfectly square, but it's only off by about 1 millimeter. So it's perfectly good for these projects. Some of the advantages of these origami projects is you don't have to bring glue or scissors to class. You end up with a really pretty object when you're done, which the kids are really proud of making. If you're concerned about like, oh well, this isn't, high level enough, you should realize that paper folding is mathematically equivalent to straight edge and compass construction. So if you feel that straight edge and compass constructions are a high enough academic level for your students, then this is a reasonable substitute. You can actually do more with the paper because you can fold out into 3 dimensions, which you can't do with the compass and straight edge constructions. Some of the downsides are if you would rather have them cut and paste a whole bunch of little 3-dimensional objects, you're not going to end up with a big pile of objects when you're done. You can only end up with maybe 1 or 2 objects because the time is not going to be there to make a huge collection of these things. I'm going to just show you real quickly what it looks like as you fold these. Fold the paper in half, fold the paper in quarters, and fold the tip up and do this kind of thing to the paper, just like that. And then you have to tuck the one corner in. This tuck ends up being harder than you would think because the students are having trouble visualizing it at this point. But it's really the same way when you fold over a cardboard box. You fold the flaps over. So it's really something they've done before, and they have to make that connection that this step is really familiar territory. And once they get that, it's not a big deal. Okay, this is just an artistic flourish that's not important to the mathematics of the discussion, but these little tips can get folded over and they look really pretty. Okay, so what we have here, if you look at the shape we have, it's really a square with 2 half squares attached. You have this parallelogram, or you can think of it as 4 45, 45, 90-degree triangles, all of the same size. And so that's what you want to have burned into your head. That's what that shape is really doing for us. So when we go to assemble the object, you should realize that at the obtuse angle on this parallelogram, that's where the hyperbolic vertices are going to show up. The ones that have the 5 pieces coming together. It looks like a ruffle. And the elliptic vertices are the ones that look like pyramids. They have 3 pieces of paper coming together. Those are going to occur where those green circles are. Okay? All right, so you flip this thing over, keep folding it, and you put little creases in it. And those corners that are popping out, those are the ones that are going to turn into the pyramids, and those corners that are basically sitting on the table, those ones are going to turn into the hyperbolic vertices. Okay, so you make 30 of those. It probably takes about an hour for the first time you do it. It's a little faster the next time. And now I want you to see how they connect. So this black unit, I'm going to say let's say is the reference unit. It's going to touch 4 other units. So in the middle of this black unit, you see there's these 2 pockets. And their purple unit is sliding into the top pocket, and then the colorful unit, the flowered unit, is tucking into the bottom pocket. And so that's how the black unit accepts 2 other units. But the black unit has 2 tips of its own, and they tuck into 2 other pockets to 2 other units. So each unit receives 2 units, and each unit tucks into 2 additional units. So each unit touches 4 other units. Okay, so the way we're going to make this hyperbolic vertex, I just want to show you, you sort of just tuck one, like the flowered one gets tucked in, and I wanted to just point out again, we are actually forming a pyramid. I lied. That's a pyramid we're forming. And the blue circle is showing you where the hyperbolic vertex is going to go. Okay, so I'm going to actually build the hyperbolic vertex now. And again, as you build the hyperbolic vertex, you see that it's very close to a whole bunch of other elliptic vertices or pyramids. One is missing on this diagram because we haven't put the last piece of paper in. And that's what it looks like when you have the first 5 pieces stuck together. And then you just keep building, and I'm just going to flick through these really quickly, and your hand starts to figure it out. And then you have your unit completed. Great. Okay, so what is this Shinobi project good for? Okay, first type of problem I like to show my students is this: it's connected to the duality of regular polyhedra. Well, what does that mean? So if you start with a cube, you can put an octahedron inside, or vice versa. So let's consider the cube, which is the one with the green octahedron inside. If you put a point in the center of each face of a cube, and then you connect with edges all the faces that had adjacent sides in the original diagram, you just end up with the dual object from what you started, and then you just alternate back and forth. So you think of it this way: the cube has 6 faces, so the octahedron has 6 vertices, and vice versa, right? So the cube has 8 vertices, so therefore the octahedron has 8 faces. The same exact relationship exists with the icosahedron and the dodecahedron. The icosahedron has 20 faces, but it has 12 vertices, and the dodecahedron has 12 faces and 20 vertices. Okay, and unfortunately there's only one of these objects left, so the tetrahedron has to be its own self-dual. It has 4 vertices and 4 faces, so that makes it work out. Okay, so what does this mean? If we look at this object again after it's been completed, what happens? Well, I can just look at the tips of all those pyramids and connect them all together, and I get myself a dodecahedron. Or instead, I could look at all those valleys, and if I just draw all those edges, what I end up with is the icosahedron. So as the student is holding the object, you tell them this, and you say, run your finger along the edge, put your hand around the outside, feel the 2 objects in your hand simultaneously. So you can feel the dodecahedron in your hand, and then alternate. Okay, I feel the dodecahedron, I feel the icosahedron, I feel the dodecahedron, I feel the icosahedron. And then you get that sense of what it means to be a dual. Another way is that if you happen to bring a soccer ball in, I don't happen to own a soccer ball, but if you do, this would be a good time to bring in the soccer ball and show, like, if you start with a dodecahedron and you just, start with an icosahedron and you just shave off the corners until they turn into little pentagons, and you end up with your soccer ball. This is what the object looks like if you start with the icosahedron and build up from there. And this object uses 90 pieces of paper, and it's kind of built around a dodecahedron, but not quite. It's a dodecahedron that's been subdivided into a triangular mesh, and then you build up from there. Okay, so how much paper do we need? For the tetrahedron, you need 6 units, but when you build up the tetrahedron, the object you get is a cube. It's kind of confusing, but you have to start with a triangular mesh grid and build up from there. So if you start with an an octahedron, then you get, you need 12 pieces of paper. An icosahedron, you need 30 pieces of paper. The reason you have to multiply by 3/2 is that each pyramid requires 3 units to come together. However, each unit is used in 2 pyramids. It makes more sense to count based on the pyramids than to count based on like the hyperbolic vertices, because the ratios of the paper are going to change for all these different objects for the hyperbolic vertex, but the elliptic vertices are the same for all these objects. So it's easier to just count the paper based on how many little pyramids are sticking out. Okay, next problem to talk about with your students, we've got Euler's chi for classification. What's Euler's chi? In case you don't remember, chi is, in this case, vertices minus edges plus faces. And that is kind of self-explanatory if you know a little bit about what's going on. Let's see, chi equals 1 anytime you have a single component with no holes. And that works in any dimension, but you have to alter the formula. For example, let's go up to 3 dimensions. In this case, we have an object with a hole, so chi is going to be 0. But you just add up vertices, edges, faces. But now that we're dealing with a 3-dimensional object, you have to count the number of 3-dimensional volumetric units. And since I've already used the letter V, I'm using B for blobs. That's what I use in my class, because I've already used V for vertices. Anyhow, you have to alternate the signs as you go up in dimension, and chi is a topological property that can extend to as many dimensions as you wish. Okay. So what about this object? This is just what the cube looks like. It has 8 vertices, 12 edges, 6 faces, and you still get chi equals 1 because it's a single solid unit with no holes in it, so it's topologically equivalent to a sphere or a pancake or whatever that has no holes in it. So chi is going to be 1. This is what the object looks like if you base, listen, this was based off of, that's a cube. This one is the object that's based off of the octahedron. And of course we're going to get chi equals 1 for this guy. And for this object, this is your standard synobi that's based off of an icosahedron. Of course you get chi equals 1. And what about, okay, the next problem I like to show my students, angle deficit for topological classification, which is of course entirely different from the one we just did. Of course it's the same, but we don't tell them that right away. Okay, so what about for the cube? I'd like to alternate between the 2 different diagrams, between a picture of something that's fully assembled and one that's flat. In real life, if you have the object, this isn't necessary, but if I'm showing you on an overhead or printing something out, it's much easier to see the angle deficit in a flattened diagram, and it's much easier to count the vertices in a constructed object. So here we've got 8 vertices. The total angle deficit is 90. You multiply that together and you get a total angle deficit of 720 or 4 pi. Next example. If we have a cuboctahedron, if we look at the template, it's very easy to see that each vertex has 60 degrees missing. And if you look at the constructed picture, it's very easy to see that there are 12 vertices. So 12 times 60 gives you 720. Bing, we get the 4 pi again. And the same thing works with our synobi. But then you get to tell them, hey, guess what? Total angle deficit is 4 pi times chi. So that's a big thing to, sort of reveal. Like, you have 2 completely different ways of calculating the same quantity, and that's pretty cool. Okay, and let's not forget the Gauss-Bonnet theorem. What does that say? Well, if you trace out a closed curve on a surface, the total enclosed Gauss curvature, which is our total angle deficit, is 2 pi minus the total angle defect, that is the angles of deflection, as you travel around the curve. So as we travel around in a positive direction, what I'm assuming here in this diagram is that we're always traveling on a geodesic path. That means it's just, you're not putting any force or pressure into, you know, changing the direction of your wheels, let's say. You're just going in the direction that the curve takes you. But every so often you make a conscientious effort to correct course. And when you move intentionally and move the direction of your little wheels, that deflection is recorded. And so in this diagram we have angle defects of pi over 4, pi over 8, pi over 2, etc. You add those guys up. And what is our Gauss curvature if you add up pi over 8, pi over 4, 3 pi over 8? Well, just trust me, these numbers add up, and the total Gauss curvature does equal 2 pi minus the total angle defect in this diagram. Okay, so what about this? So let's try to see if Gauss-Bonnet theorem makes sense on a very simple example. Let's take a sphere and put some kind of equator around the sphere. The total angle defect has to be 0 because we're using a geodesic. That should tell us that off to one side, if we're traveling around, like whatever direction you're orienting this curve, you're going to look off to the left of it. And the total Gaussian curvature must be 2 pi on that side. That's what the formula says. Well, it has to be true, right? Because since this is symmetric, you can just change the orientation of the curve, and then the other half of the sphere must also contain the same angle, the same Gaussian curvature, and it works out. So each half of the sphere contains 2 pi Gaussian curvature. And of course that works just fine if you use a soup can, same exact thing happens. What about a Rubik's Cube? Okay, now that's something that we can be a little more concrete about, because now we have the same geodesic circling half of this object, and you still get 2 pi on each side of this object. It doesn't look symmetric, but trust me, it is. If you pick this thing up and you know, look at it, it looks exactly the same from the opposite direction. Each half contains 2 pi. But now, since we've made everything discretized, like all the Gaussian curvatures are now accumulated in specific points, as opposed to over here the curvature was spread out smoothly over the whole object. In this object, the curvature was accumulated on the rims of the cans, but now we've accumulated it into specific corners. And then we can just say, hey, look, 2 pi has to be accumulated equally in each of these 4 corners, and it is. It's pi over 2, which we can actually count now. We can say, aha. So there's pi over 2 missing out of each of these vertices. So everything works out. So Gauss-Bonnet works. And just to say, Gauss-Bonnet works on other objects too, but I'm just not going to worry about them. But if you want to check my arithmetic, I'm just throwing in some extra examples for you because they're fun. But trust me, they all work out. And in these cases, we actually do have angle defect. We're on geodesics on the straight line segments, but we do have angle defect at the corners of these shapes of these paths. Okay, but back to another geodesic. I like geodesics. Okay, so in this case, the total angle defect is 0, and you still get 360 degrees on either side of this curve. But I really like this example because even though topologically we're cutting the object in half and putting 360 degrees on each side of the curve, obviously geometrically we are not cutting the object in half. So that gives rise to yet another little classroom puzzle, which is how many different geodesics can you find that topologically cut this object in half? And so that's a fun thing to explore if you want to. Okay, bonus puzzle. Last thing is, can you take 30 pieces of paper with 3 colors, 10 pieces of each color, and can you assemble it such that at each pyramid you get 1 of each color? And the answer is yes, you can do it. Okay, so if you want to visit my website, it's donnadietz.com, and you can look at my Sonobi videos if you want. But I'm sure that you didn't catch everything I said. So if you want to look at my slides, go to my website. This is not an advertised link, by the way. You can just, you guys can find my slides here, origami.pdf. or you can send me an email. And hopefully some of you enjoyed some of that.